All right, so let's finish up section 9.2. And I just want you to remember first how we represent a point in polar. Okay, you have a radius and you have an angle. Okay, and before I graph this on the calculator, I want to think about what it might look like. Okay, it says to graph r equals 2. Now, if you have a point, usually they give you a radius and an angle. They're only giving me a radius. So the angle could be anything I want. So if I graph every single point that has a radius of 2, any angle that you want, what shape would it end up making?
A circle.
Yeah, it's going to make a circle. Okay? And that's one of the advantages of using polar. It makes drawing circles extremely simple. Right? So all we have to do is, on your calculator, go to mode, go to polar. And now it's going to say r equals. Okay, anytime you graph in polar, you have to get r by itself. Just like when you graph as a function, you have to get what letter by itself? Y. So type in r equals 2. Okay, and remember we talked about the screen. If you want to get that zoom to look right, you can do zoom square. And let's take a look at why it's not graphing. Okay, I know why it's not graphing. So our window's fine. Okay, all I really need to do is go 2 units left and right, 2 units up and down. But the problem is my parameter. Okay, it's only graphing from 0 to 6.28, which would be okay if I was in radians. But in order to see a full circle in degrees, how many degrees do I have to graph? I have to go all the way to 360. So theta is kind of like a parameter. So instead of a T-min and a T-max, now you have a theta min and a theta max. Okay, it is drawing it very, very slowly, and that's the next thing I'm going to get at. Why do you think it's drawing it so slow? The theta step. Okay, the theta step is probably set.
It's set to point.
Yeah, it's set to 0.13. Okay, I don't really think I need to graph every single angle from 0 to 360 going by 0.13. That's thousands of points. Yeah, I think if you graph every angle between 0 and 360 going by 5s, you'll get a pretty decent circle. I don't think you're going to get it much smoother than that. All right, so any questions on that? It's very, very similar to parametric. Set your theta step correctly, not too low. For example, if I did it at 90, how many points would it graph now? 5. 0, 90, 180, 270, 360. And 0 and 360 would be the same, so it's basically going to look more like a diamond. Okay? So I would say 90 is a little too high for theta step. You might even be able to get away with 10. I think it looks okay. You might notice it if you start to zoom in a little bit, but it doesn't look as smooth. But actually, no, that looks pretty good. Okay. So 10 is actually okay. Any questions on graphing a circle in polar? All right. How about if I graph this? This time, they're not telling me the radius. I want to graph every point that has an angle of 2 radians. This one I can't show you on the calculator. What would that look like? The radius can be anything you want, but the angle has to be 2 radians. Yep.
It would just be a straight line out from the origin.
Yeah, just got to be a straight line. Just to get an idea of how many degrees that is, let's convert it. I'll multiply by 180, divide by pi. So that's 360 divided by pi it's roughly 114 degrees. So I want you to graph every single point that has an angle of 114 degrees and a radius of 2. No, radius can be anything we want. Okay. So let's go out 1 unit and go 114 degrees. 2 units, 114 degrees. Okay. 3 units, 114 degrees. Right, so we get a line basically like that. Now, what other kind of number could the radius be? Besides, I did positive 2 each time. It could be negative 2. So if we went, or negative 3 or negative 4, it could be negative anything. Right? So if I went left and then went 113 degrees? It would end up right there. Could go left 2, and then again go around that same degree measure. Left 3, same degree measure. So I get a line that's going to extend in each direction. Okay, so that's the radius can be anything you want as long as your angle is 2. Okay. Any questions on that? So graphing lines to the origin, not too bad. But if you wanted a line with a specific slope and intercept, that would be a little harder. How would we do that in y equals form? What's our equation for a line in y equals form? Y equals mx plus b. Now in polar, you don't have what letters in that equation? You don't have the x and the y. Okay. What did we say yesterday y is equal to? Theta was part of it, but there was more. When we were converting from polar to rectangular, what was y?
R sine theta.
Y was r sine theta. Okay, we just got rid of y. And what was x?
R cosine theta.
R cosine theta. Okay? Plus b. So all I did was change x and y to the 2 expressions we had yesterday. Any question on that? Now, to graph in polar, what letter has to be by itself? R. So I'm going to move everything with r to one side. So we've got r sine theta. And how would I move this term to the other side?
You have to divide by n.
Remember, it's a plus b on the end, so we can divide there. Subtract, right? Just like if you had 2 equals 3 plus b. If you have a plus, you want to move that, you subtract it. Right, so we'll subtract Mr. Cosine theta. And now, what do both terms have in common?
The R.
The r. So I'm going to factor that out. What would be left in the second part? Just m cosine theta. And now, how would I get r by itself?
Divide both sides by sine.
Yep. Now I would divide. b divided by sine theta minus m cosine theta. Now, theta is a parameter. In order to get a full picture, you just let it go from 0 to 360. M is your slope. B is your y-intercept. Right, so somebody give me an equation in y equals mx plus b with a number for both slope and intercept. Right, so that should be in a line with a slope of a half, y-intercept of 3. I'm going to fill in a half for m. I'm going to fill in 3 for b. And if I do this right, that's how it should look in polar, just like you would expect it as a function. Let's try it. Let's bring this back up. All right. So I'm going to type in, let's look at my equation. It's b, Okay, what did we say the intercept was? 3. Divided by sine theta minus m cosine theta. So sine theta minus, what was our slope?
1/2.
1/2 m cosine theta. Right, so that looks good. So if I graph that, it should be a line with a slope of 1/2, y-intercept of 3. Let's check it out. I gotta adjust my window a little bit. Let's do zoom 6. And then there we go. So there's a line with a slope of 1/2, and there's your y-intercept right at 3. Right, so equation of a line in polar, not very nice. Okay, we already have a very nice way of doing it, y equals mx plus b. So personally, I wouldn't use polar to draw lines. I think it's kind of complicated. Circles, very, very simple. Use polar if you're going to make circles. And same thing for a function. Don't try to do circles as functions. That's a little harder. Do lines as functions. That's easier. And also, did you see how it sketched it? If you kind of watch it again, just change it. What did I change? Oh, lost my division sign. Thank you. There. See how it sketched it? See how it kind of like started at one side, it went down, and then went back up and did the other side? That all has to do with our parameter. Okay? If I did negative 180 to 180, still going to get the same picture. But watch what happens. Actually, I think it looked pretty much the same. Okay, as long as you pick anything that's 360-degree interval, you'll get the same picture. Okay, any questions on that? Okay, so there's your equation for a line in polar. So next function we're going to look at is this one, r equals 3 plus 3 sine theta. And we're going to try to make a table of values to graph it. Okay, this is a little tricky to visualize. And we're going to try to figure out what the radius is going to be in different parts of the graph. What do I have to let theta go from to get a full picture of this? What'd you say, Nick?
60.
Up to 60?
360.
360. And start where? 0. Yeah, start at 0. Okay, to go through every possible value in the sine function, you need to start at 0 and end at 360. Or if you're doing radians, 0 to 2 pi. All right, now, this is the graph of sine. Okay, so when I look at the graph of sine, I kind of see 4 different behaviors. Okay? It starts out increasing, okay, and then decreasing, still decreasing, and then it switches back to increasing. Right? So when we start to look at the radius for this function, we're going to think about sine in those 4 sections. From 0 to 90, increasing, 90 to 180, decreasing, 180 to 270, decreasing even more, and then 270 back to 360, increasing. Right? And that'll kind of help us to figure out what this is going to look like. All right, so let's look at what happens over the first interval, from 0 to pi over 2. Where does sine start in this interval, and where does it end for its y values? It starts at 0, and it ends at what?
1.
No, it doesn't end at 0.
Ends at 1.
Ends at 1. Yep.
That's when you push down.
So over the interval from 0 to pi over 2, your sine function goes from 0 to 1. So now let's figure out what's going to happen here. If sine starts at 0, what's the sine of 0? Oh, I'm sorry, we already got that. Sine, starts at 0. So 0, what's 0 times 3?
0.
Plus 3?
3.
3. Okay, so my radius is going to start at 3, and it's going to end, well, sine goes up to 1. What's 1 times 3?
3.
And 3 plus 3?
6.
6. So in this section, the radius of this graph is going to change from 3 to 6 as sine goes from 0 to 90. Okay? So we'll just write that down and we'll try to sketch it after. So it's not a circle. The radius is changing. Okay, but it's not going to be like a spiral either. Okay, what happens to the sine function from pi over 2 to pi?
It goes from 1 to 0.
Yep, it decreases from 1 to 0. So let's see what happens to my radius. What's 1 times 3? 3 plus 3? 6. And now sine is going to go all the way down to 0. So when sine hits 0, what's 0 times 3?
0.
Plus 3? Okay, so in this section, my radius is decreasing from 6 back to 3. And you're going to see some symmetry here. All right, next section. What happens to my sine function from pi to 3 pi over 2?
It goes from 0 to -1.
Yeah, this goes from 0 till it hits its lowest value at -1. So my radius is going to go from 3 times 0 is 3 plus 3. And then -1. 3 times -1 plus 3 is what?
0.
0. So in this section, my graph is actually going to be having a radius of 0 at one point, which means it's going to touch the origin.
So it's exactly the sine function just expanded. Is basically what this is.
It's not going to look like a wave when we graph it.
So it's not going to look like
Nope. It's going to have a really different shape we've never seen, at least in this class. Okay. What happens to your sine function as you go from 3 pi over 2 to 2 pi?
0.
We go-
1 to 0.
You go from -1 back up to 0. Right. What's 3 times -1? Plus 3?
0.
So my radius is going to go from 0 to 3 times 0
0.
plus 3.
3.
So my radius is going from 0 back to 3. All right. Now, keep in mind here, you're going to see some symmetry. Okay, so we'll use that to help us sketch it. And since the sine function is not linear, when I start to draw this out, nothing here is really going to be straight. It's all curved. All right, so let's see if we can sketch it. All right, as I go from 0 to 90, I need to have my radius expanding from 3 to 6. All right. So here's 0. Here's 90. Okay, or if you want to do it in radians, 0, pi over 2. And my radius, what does it start at in the 0 to 90 section? It starts at 3. What's it end at? 6. And we need to connect those 2 points. But they're not connected straight. Okay, it's going to curve kind of like this. So the radius, as your angle starts to get bigger and bigger, let's see what's happening to your radius. The radius is getting longer and longer. Okay. Now, what happens to my radius in the 90 to 180 section? Yes, as you go from 90 over to 180, it's going to come back down from 6 to 3. So, and it's actually a mirror image. So I'm just going to take this, clone it, flip it. And it's, notice if you were to draw in your radius, As your angle gets closer and closer to 180, the radius is shrinking down until it's finally just 3 units long. All right, next part. What's my radius doing from pi to 3 pi over 2? It's going from 3 to 0. So it's going from 3, and as I head to 270, it's wrapping in towards the origin. Okay, it's going to shrink all the way down to 0. Okay, and then what happens in the 270 to 360 section? Yep, it's expanding back out to 3, okay, 0 to 3. So that's really, again, a mirror image of this. And if I drew this right, maybe you can tell what it is. It's upside down, but that's how this one. Yeah, it kind of looks like an upside down heart. My drawing's not perfect, but if you can tell that, I'm happy. Okay. So that shape is called a cardioid. Okay, and it's called a cardioid because it looks kind of like a heart. Okay, let's sketch it on the calculator and see what it looks like there. Okay, so we've got 3, oops, let's clear that. 3 plus 3 cosine theta. What did I type in? Oh, 3 plus 3. Well, that's actually a good mistake I made. Notice what happened when I put in cosine accidentally instead of sine. What did it do to the, my window's a little distorted, but what did it do to the heart shape? It rotated it. Okay, so if you accidentally put in sine instead of cosine, it will rotate it. Okay? Okay, so anything of that form, okay, if you put in a number plus or minus the same number sine theta, and then a number plus or minus the same number cosine theta, as long as you don't use 0, you get a cardioid. Now, interesting things kind of happen if you make these numbers different. Okay, to be a cardioid, they have to be the same. But if you make one of them different, watch what starts to happen. Like, make this a 5. So that's not a cardioid, but the shape starts to loop back on itself. Okay? And the further apart these numbers get, the more you'll see it looping kind of on itself. Okay, but for a cardioid, you have to keep those numbers the same. Okay, I told you the parameter only has to go from 0 to 2 pi to get a complete graph. What would happen if I went beyond 2 pi or beyond 360? Yeah, it's just going to trace over itself. So if I take this, let's make it 0. What if I wanted to trace over itself twice? If I put in 720, okay, it's going to do once, and it's tracing over itself a second time, but you can't see. Okay, so any questions on graphing cardioids? Okay, not too bad once you recognize the format. Okay, so anytime you see something in one of those two forms, you know it's a cardioid. Hey, does everybody have that? All right, so next thing we're going to look at is how can we change something from polar into rectangular. Well, I just did an example with you guys going the other way. I showed you how to take something that was a rectangular equation, y equals mx plus b, and change it into a polar. Well, to go the other way, we still use the same formulas. Okay? X equals r cosine theta, y equals r sine theta. We could use r squared equals x squared plus y squared, and theta equals inverse tangent y over x. Okay. Those are the four basic formulas we can use to change between rectangular and polar. Okay. In other words, these are the only relationships we have between x's, y's, r's, and thetas. So the next thing we're going to do is look at how can we change a cardioid into rectangular. Okay, we're not going to try to graph a cardioid in rectangular. You'll see why. Okay, we're just going to take that equation, which again, pretty straightforward, just 3 plus 3 sine theta, and I want to change it to rectangular. Right, so to make that rectangular, ultimately, what do I have to get rid of here? R's got to go away, and the sine theta has to go away. Okay, my goal is to have all x's and y's. Let's start with the sine theta. Do I have a formula up above that I can use to substitute in something for sine theta?
Yeah.
Yep. What is sine theta equal to?
Y over r.
It's y over r. Now eventually we have to get rid of the r, but that's at least a step, and then we'll just have all r's. We'll work on that. So sine of theta is what again? Y over r. Okay. Now I have to get rid of, well, actually, you know what we could do here too? Just to simplify it, what could I multiply everything by to get rid of this denominator? Yeah, let's multiply all terms by r. Okay, that's just going to make it look a little neater. So what would I have on the left?
2r.
R squared equals plus 3y. I think that just looks a little nicer than the last one. But now, what do I have to get rid of?
The r's.
The r's. Do I have a formula for r squared? Yep. What is r squared?
X squared plus y squared.
Squared plus y squared. Now I need to know what's r. Could I plug in for that?
Square root of x squared plus y squared.
Yeah, the square root of x squared plus y squared. And what's still on the end?
3y.
Plus 3y. Do I have any r's left in that?
No.
Nope. Any thetas? Nope. So that is now rewritten in rectangular. I'm not sure if we could actually graph it, okay? Because to graph, you have to get y by itself.
That's not so good.
And, okay, we've got y in several spots, so
There's no y.
Too many Y's, man.
it'd be hard to get y by itself. Okay, so point here, if you want to graph certain shapes like a cardioid, okay, very simple in polar. Not so simple as a function.
Yeah, just
It's actually not even a function. It fails the vertical line test. Okay, questions on?
So that's your final answer.
Yeah, that's all we can really do. As long as we get rid of all the r's and thetas, that's all you have to do. Okay. So on your reference sheet, you might want these formulas. Okay, you'll need them on the test. All right. So that's how you can change from polar to function. Okay, I showed you earlier with the equation of a line, function to polar. Okay, now we're going to convert polar to parametric. So I drew a curve in polar. Okay, this could be any shape you want, just some kind of curve. Doesn't even have to be a function. And basically, all we have to do is create a triangle. It's just the hypotenuse is not fixed. The hypotenuse is constantly changing, okay, depending on where you put your point. Okay? If this was a circle, the hypotenuse would always be the same. I could just give you a number for it. In this case, I can't give you a number for the radius or the hypotenuse, but I can give you a function for it. Okay? So we don't know the equation specifically. Let's just say this is r equals some function. And why am I using t as my variable, not theta? Because we're going to be changing to parametric. Okay? So that's why I'm introducing t. Okay? So this curve you see right here is generated by this formula, r equals f of t. Some function, we don't know what it is. Okay? So then what I did from there is just pick any point you want along the curve. Okay, just put a point. And I want you to make a triangle out of that point. Okay, and that coordinate, when you change it to parametric, it's going to have an x value, and it's going to have a y value. I'm no longer going to care about what is this radius and what is this angle. Okay? I'm not going to care about that. And to represent my angle, I used t. Okay, t. How long is this bottom side? It's x. And how about the height? Is y. All right, so now I want to try to break up this point into an x value and a y value. That's how we make it parametric. Right? I no longer care about its angle and its radius. That's polar. I'm its x and its y value. So what trig function would I use to get an equation for x?
Cosine.
Yep, cosine. And it would be cosine of what?
T.
T equals
Y over R. No, it's X. X over R.
x over r. Now remember, is r fixed? Is every point in that curly thing I do a fixed distance from the origin?
No.
No. So where we have a formula, we have to fill in for r. Okay, r equals f of t. Okay, and let's do that right now. There's some function that's going to generate r for you. You will be given that function when we do an actual problem. All right, and how would I get a formula for y?
So
Sine of t equals,
Y over function of T.
yep, it would be y over r. But again, r is not a fixed value. You're going to have a formula that tells you what r is, and it can change. Okay, if it's anything but a circle, r is never fixed. All right, so now let's get our formula for x. What will x equal?
F of function of T cosine T.
Yep, x equals f of t cosine t. I already have it written, so I'm not going to write it again. And how about sine.
F of t sine t.
F of t sine t. So to take something that's in polar and make it parametric, you have to do two things. One, change all your thetas to t's, because when you're in parametric, you use t. Okay. And then to write your x function, take your function after changing everything to t's, multiply it by cosine. To get your y values, take your function after you change everything to t's and multiply it by sine. That's going to break that hypotenuse into a horizontal and vertical component, if you want to think of it like a vector. And f of t is kind of like the magnitude of your vector. It's the length. Okay, so again, this converts from polar to parametric. All right, so I'll leave those up. And let's try to just convert this. We're not going to look at the picture yet. Okay, I'm going to show you that after. Here's f of theta. Okay. Here's your function that's generating the radius. Okay. The formula is 7 sine 2 theta. So the first thing I have to do is change my thetas to what? T's. Right, so now I'm just going to write down below f of t equals, what would that look like just changing theta to t? 7 sine 2t. Okay. Here's your function that generates the radius. But you want to now separate the radius into your horizontal and vertical components. So what do I multiply this by to get the horizontal component? Yep, cosine t. So 7 sine 2t cosine t. And what do you multiply your radius by to get just the vertical part? Sine t. Don't try to do sine squared or anything fancy because the arguments are different. Right, so 7 sine 2t sine t. Right, now I'm going to graph the polar and I'm going to graph the parametric and show you that they come out the same. Right, so let's graph 7 sine 2 theta. We'll talk more about the shape after. Okay, let's try zoom 6. Okay, so that's the first one. Okay, and that was, I'll put it underneath. Actually, you know what? Let me just write polar. And now let me do it in parametric. So go to parametric. For my x, type in 7 sine 2t cosine t. Multiplying by the cosine gives me just the horizontal. Okay. And then take the same thing. Yep, and multiplying by the sine of t gives me just my vertical. Right, let me adjust my parameter. Let's go by 0.5. I want to see how that looks. Okay. Oh, and what should my what's my mode on my calculator?
Your mode is degrees.
I'm in degrees. So
You need 0 to 360.
if I'm going in degrees, I got to go 0 to 360.
And then you should, instead of 0.5, do 10.
Yeah, 10 will probably be okay. So that'll block here, but
And maybe try 5.
yeah, if you went by 5, it would probably smooth it out a little bit. Okay, and that's parametric. Okay, so exactly the same picture. One's polar, one's parametric. Okay, any questions on how to change a polar graph to parametric? Just take and change theta to t, multiply it by cosine to get the horizontal, multiply by sine to get your vertical. Hey, let's look at the picture a little more. Okay, and let's look at it in polar. Just quicker for me to change things because it's a smaller equation. We had 7 sine 2t. Anybody think they have a guess what either the 7 or the 2 affects in that picture? And if, what do you think the 7 does?
It affects like where it moves or how it moves.
All right, let's try changing it to 3. What did that affect? The size of it. Okay. And if we call each one of these like a petal, like as a flower, it affected the length of each petal. How long do you think each petal is now? It is. It's 3 units long. Okay. If you change it to 8, each petal would now be 8 units long. So what do you think this 2 has to do with? Changes what?
The orientation of it, like how it versus.
Like rotating it? Okay.
I was saying orientation, not rotation, like how it's actually laid out, like the shape it takes.
The shape of the, so still the same number of petals, just changing how they're laid out?
I believe it's just how it's laid out, yeah.
Okay. Any other guess what the 2 might do?
Will it change its height?
The only way we can change the height is the
changes
7.
Scale. 7 changes
Yeah.
the kind of scale.
Well, let's try making the 2, pick another number. Let's try 4.
Oh my gosh.
So what did that do?
Make a flower.
The amount,
Amount of what?
the amount else.
Amount of petals. So what do you think the relationship is between the argument and the number of petals you get?
It's double whatever the number you plugged in, because it changed. It was 4 for when you had 2, and now it's 8 when you have 4.
Okay, so that seems to make sense. You double the argument. If you take the argument and double it, that's how many petals you get. Let's try 3 theta.
Whoa.
So thoughts now? Let's try 6 theta. How many petals did we get there?
Yeah.
12.
Okay, so that's back to the original pattern. If you plug in 6, we get 12. So what's the...
Is it evens and odds?
It has to do with whether it's even or odd.
Oh, try 1.
Let's try, yeah, we'll try 1 in a second. 5, I can't show you. I think that's going to be something strange, though.
Oh, so it's
So if you type in an odd number, you get exactly that number of petals. If you type in an even number, you get that doubled.
Oh.
Yep. So if you
even double.
So if you type in just 1, let's see what happens.
That's what I thought.
I think we just get 1. Okay, so those graphs that we were looking at, those were what the book calls a 4-petaled rose. Okay, that's what it's a picture of. As long as you keep your argument at 2, the absolute value of the number in front is the length of the petal. Okay, so what I might do on a test is give you an equation and ask you how long are the petals. Okay, you just take the absolute value of the number in front. Now, we used sine for these. What do you think would happen if I use cosine? Yeah, it's going to rotate it how many degrees, you think? Well, let's try it. Right. So instead of typing in sine, I'm going to change it to cosine in a second. There's our 4 petals. Okay, kind of notice where they are. And let's try cosine. And now they're there. Okay, so it rotated it. Yep, it rotated it 45 degrees. Right, so you could do all kinds of things. You could, if you try decimals, you get kind of just funky shapes. It just does weird things on the screen. Like, try like, you might get pedals that don't complete, right? Things like that. Okay, this pedal, you got like half and half a pedal. But still a lot of symmetry there. Okay. And you can play with it and get all kinds of different graphs. Okay, so any question on how to explain to me how many pedals you get or how long the pedals are? Okay. All right, why is this going to be a spiral? Why wouldn't it be a circle?
No set radius.
Yeah, the radius isn't set. The radius is equal to whatever the angle is. So if you did it in degrees, at 0, the radius is 0. At 10 degrees, the radius is 10. By the time you get to 360 degrees, the radius would be how long? 360. So you need a pretty big window to see it. Okay, let's graph this spiral over these different intervals. All right, so just type in r equals theta. Let's go from 0, I'm going to change to radians, 2 pi. Let's change to radians. Anything else that I should adjust on my window if I'm now in radians? This won't graph. If I hit graph, it's not going to work.
Your step.
Yeah, what should my step be?
Probably like 0.5.
Yeah, point 0.1, 0.2, 0.3, anywhere in there, because you're only going from 0 to 6.
You have 62 points on it if you had 0.1 now.
Yeah, if you did 0.1, it would be graphing around 62 points. But it's a very simple function. There's no sines or cosines. So I think it'll be OK. Now, what's the biggest that my radius is going to spiral out to? 360. Over this first interval, what's the longest my radius could ever be? 2 pi, okay? Or 6.28. So I think negative 10 to 10, negative 10 to 10 should be perfect. And it drew the spiral pretty quickly. Okay, so that's your picture from 0 to 2 pi. All right, let's do it from 0 to 4 pi. What do you think is going to happen there?
Goes around the spiral.
Yep, spiral's just going to continue. Now, what's the biggest that my radius on my spiral is going to be?
4 pi.
It can go all the way out to 4 pi, which is about 4 times 3, about 12. So maybe we should go negative 15 to 15. Now, keep in mind, your spiral doesn't come close to hitting the maximum in every direction. Okay? It's really only on kind of where it ends. Okay, so if we go 4 pi, it's going to come the farthest out on the positive x-axis. So we might be able to get away with just making that one bigger. Okay, let's see if that works. Not quite. All right, we got to make the y-max y-min a little lower. But I know it can't go beyond negative 15. In fact, it won't even come close to the edge of the screen now. Okay. So there's 0 to 4 pi. Okay, and if I were to do 0 to 8 pi, what would happen there?
Just go.
How many more times? 2 more. Right? Go around 2 more times. Okay. What do you think is going to happen if I graph it from negative 4 pi to 0? We'll compare that from 0 to 4 pi. What do you think it'll do to the spiral?
Twist it a bit.
Twist it? What do you mean by twist it?
Turn it. Or reflect it over. Reflect it over the y.
Reflect, so like it'll be like a mirror image. As we drew it, did anybody note the direction it was spiraling in?
It was spiraling counterclockwise.
Yeah, it was spiraling counterclockwise.
Counterclockwise.
Well, we can see. Let's see if it changes the direction, or maybe it does a mirror image. Let's try it. So negative 4 pi to 0. Okay, and we kind of have to watch it as it goes to see the direction if it changes. Did it change direction? No. Okay, let me make the window a little different.
It started from the outside instead of the
Yeah, it
inside.
started out there because that's what I wanted.
Yep, it did start. It started from the outside, but it didn't trace this spiral just starting from the outside working in. Are these two spirals the same?
No, they're the same proportion, but they're reflected.
Yeah, it looks like a mirror image. Okay, they're mirror images of each other. So not only does it start spiraling from the outside in, but it mirror image. It reflected it over the y-axis.
It's just like shaped differently because of the window, right?
Yeah, the shape might look a little different because my window's not. I can see the tick marks are not spaced exactly the same. But yeah, it's the exact same shape. Yeah. Okay, and then negative 8 pi would be the same spiral, starting from the outside, making 2 more revolutions in towards the center. Okay, so changing the parameter did 2 things. 1, reflected it over the y-axis. 2, it caused it to spiral outside in instead of inside out. Okay, so on the test, I might give you different windows and ask you to play with it and tell me how does it change the graph. Okay? Both as it's drawing it and the final picture. Okay? You might want to think how you could make it go spiral the other way instead of counterclockwise. How could you make it spiral clockwise? Okay? Think about maybe how you would just play with it and see if you could figure that out. All right, so homework tonight, it's on 493, and it skips around a little bit. So 19 to 22, and then 24, 25, 30, 31, 33, and then 37 to 41, just the odds, and 43 to 49, just the odds. Okay, so tomorrow we'll start section 9.4, which is on parabolas, okay, all about a conic section. And that will be our last section, and then we have our test on Friday.